Hey everyone, welcome back to Instrumentation Lectures. When an input is applied to an instrument or a measuring system, the instrument or the system cannot take up its final steady state position immediately. On the other hand, it takes a while for the output to stabilize and reach its final state. This interim phase is called transient phase. Some measurements are made under conditions that sufficient time is available for the instrument or the measuring system to settle to its final steady state conditions. Under such conditions, the study of transient response of the system, that is, the behavior of the system under transient state, is not of much importance. Only steady state response of the system need to be considered. It is under such conditions we study the static characteristics of the system, which we covered in the last video. However, in many areas of measurement system applications, it becomes necessary to study the response of the system under both transient as well as steady state conditions. In many applications, the transient response of the system, that is, the way system settles down to its final steady state conditions, is more important than the steady state response, especially in cases where the inputs vary rapidly with time. The behavior of the system under such conditions is described by the dynamic response of the system, and the characteristics associated with dynamic response is called dynamic characteristics. In this lecture, we will study the dynamic characteristics in detail. The main dynamic characteristics are speed of response, lag, fidelity, and dynamic error. Of this, the speed of response and fidelity are desirable characters, while dynamic error and lag are undesirable in a dynamic system. So, these two are desirable characters, while these two are undesirable characters. Okay, let us now see what is meant by each of these terms. First one is speed of response. It is the rapidity with which an instrument responds to changes in the measured quantity. It basically tells us how fast the measurement system reacts to changes in the input variable. The speed of response is quantified by the term response time. Response time is defined as the time required by the instrument to settle to its final steady state position after the application of an input. Okay, next parameter we have is measuring lag. Measuring lag is defined as the delay in the response of an instrument to a change in the measured quantity. This is of two types, retardation type and time delay type. In the case of retardation type, as soon as there is a change in the measured quantity, the measurement system begins to respond. On the other hand, in the case of time delay type, once the input is applied, the response of the measurement system starts after a dead time and thereby causes dynamic errors in the system response. Anyways, measuring lag is usually quite small, but it becomes highly important where high-speed measurements are required. In such systems, it becomes essential that the time lag be reduced to minimum. Next dynamic characteristic is fidelity. Fidelity is the ability of the system to reproduce the output in the same form as the input. As an example, see this time plot for an input x of t and the corresponding y of t for a system. Here, the output appears in the same form as the input and there is no distortion produced by the system. So, we can say that the system is having 100% fidelity. Also, please note that in the definition of fidelity, any time lag or phase difference between the output and input is not included. So, even if the output in this case was like this, say, we can still say that the system is having 100% fidelity because the output essentially follows the same form as input. The only thing is, it lags behind the input. Ideally, all systems should have 100% fidelity, but practically we can never achieve that. Now lastly we have dynamic error. It is defined as the algebraic difference between the indicated value of a measurand and its true value at any instant when the measurand is a function of time. So we can say that dynamic error is basically the inability of a system to adequately reproduce the amplitude of the input signal for a particular input frequency. Okay. Now, to study these dynamic characteristics, we need to develop a generalized mathematical model of measurement systems. As in so many other areas of engineering, the most widely useful mathematical model for the study of measurement system dynamic response is the ordinary linear differential equations with constant coefficients. We assume the relation between any particular input and output can be put in the form an into nth derivative of y with respect to t plus an minus 1 into n minus 1th derivative of y with respect to t plus etc. to a1 into dy by dt plus a0y equal to bm into mth derivative of u with respect to t plus bm minus 1 into m minus 1th derivative of u with respect to t etc. to b0u, where y is the output quantity, u is the input quantity, and a and b are constants which are combinations of system physical parameters. So these are constants which are combinations of system physical parameters. Typically, the dynamic response of an instrument to an input signal can be modeled in terms of zero order, first order, or second order linear differential equations. The simplest model for a measurement system is a zero order system given by a0y equal to b0u. Note that this is just a part of our general equation, that is this equation, where an equal to an minus 1 equal to etc. equal to a1 equal to 0, and similarly bm equal to bm minus 1 equal to etc. equal to b1 equal to 0. Okay, now if we rearrange this equation, we can write it as y equal to b0 by a0 into u, which is equal to k into u, where k is equal to b0 by a0 is called the static sensitivity. Now we can see that even if the input u varies with time, the instrument output follows it perfectly with no distortion or time lag. So whatever be the input to the system, be it step input, ramp input, or sinusoidal input, immediately its effect will appear at the output without any lag or phase change. Therefore, in the case of zero order systems, dynamic error is zero. That is, in zero order systems, they have zero dynamic error. A potentiometer is a good example of a zero order system. As you can see, the output voltage E0 can be written as a function of angular displacement theta 0 as E0 equal to theta 0 by theta t into E, which is equal to k theta, where k is theta 0 by theta t. Okay, next we have first order instruments. Instruments that contain a single storage element like capacitor or inductor can be modeled to be of first order, and their dynamic characteristics is given by a1 dy by dt plus a0y equal to b0u. Please note that this equation is also a part of our general mathematical model which we described initially. Okay, this can again be written as a1 by a0 into dy by dt plus y equal to b0 by a0 into u, which is equal to tau into dy by dt plus y, which is equal to k into u, where tau equal to a1 by a0 is called the time constant of system, time constant, and this always has the dimensions of time, and k is equal to b0 by a0 is called the static sensitivity. Also, please keep in mind that for any order system, k is always defined as b0 by a0 and always has the same physical meaning, that is, the amount of output per unit input when the input is static. An example of a first order instrument is a mercury in glass thermometer. The input quantity here is the temperature T of the fluid surrounding the bulb of thermometer, and the output is the displacement x0 of the mercury in the capillary tube. Now, the time constant tau and the sensitivity k of the system depends on many factors like area of the bulb, mass of mercury in bulb, the heat loss from the bulb, etc. By suitable assumptions, finally we will be able to arrive at a first order differential equation of the form tau into dx0 by dt plus x0 is equal to k into t, where, as we already said, x0 is the input and t is the output. Now, to study the dynamic behavior of measurement systems, we provide some standard signals as input and analyze the response of the system to these standard signals. The commonly used standard signals are step input, ramp input, impulse input, and sinusoidal input. The first three signals, that is step, ramp, and impulse, are used for studying dynamic behavior in the time domain, while the sinusoidal input is used for studies in frequency domain. Okay, here are the typical response of a first order system for these inputs. I'm not discussing how we obtain these responses and all, as it is beyond the scope of this course. You will study all this in detail in your signals and systems course. Okay. Now, one more term you should be familiar with is overshoot. The moving part of any instrument have mass and thus possess inertia. So, when an input is applied to the instrument, the pointer does not immediately come to rest at its steady state position, but goes beyond it, or in other words, the pointer overshoots its steady state position. The overshoot is defined as the maximum amount by which the moving system moves beyond the steady state position. In this figure, you can see that the response didn't settle to its steady state value all of a sudden. It initially went beyond the steady state value, then went below the steady state value, and so on, and finally settled. Here, this is the first overshoot, that is first overshoot or maximum peak overshoot, and this is the second overshoot, and similarly this is the third overshoot, this is the fourth overshoot, and so on. Okay, let us now see an example question related to overshoot. A step input of 5 ampere is applied to an ammeter. So we have true value AT is equal to 5 ampere. Then the pointer swings to a current of 5.18 ampere and finally comes to rest at 5.02 ampere. So steady state value or a measured value AM is equal to 5.02 ampere. This is also the steady state value. And also given that the pointer sinks to a current of 5.18 ampere. So peak value of pointer swing is equal to 5.18 ampere. Now we are asked to determine the overshoot of the reading in ampere and in percentage of final reading. Therefore, overshoot is equal to peak value of pointer swing, that is 5.18 ampere, minus measured value or steady state value, which is 5.02 ampere, and is equal to 0.16 ampere. Now in percentage overshoot is equal to 0.16 ampere by, it is asked to find as a percentage of final reading, and final reading is 5.02 ampere. For 5.02 ampere into 100, which is 3.2 percentage. Now we are asked to determine the percentage error in the instrument. We have learned in the previous video that percentage error is equal to measured value minus true value by true value into 100, which is equal to 5.02 minus 5 by 5 into 100, which is 0.4 percentage. That brings us to the end of this lecture. As an overview of what we studied in this video, first we learned about dynamic characteristics, which are speed of response, fidelity, lag, and dynamic error. Then we discussed about a generalized mathematical model for measuring systems, followed by the standard signals used to study the instrument dynamic response. Finally, we learned what is an overshoot. If you found this lecture useful, please like the video and also support us by subscribing to the channel. Also, if you have any doubts, leave them in the comments below. I will try to answer them with the best of my knowledge, or some other viewer can also help you. In the next video, we will learn about errors in measurement. Thanks for watching and have a nice day.